We'll be fine. Sorry.
Okay. Good. Yeah, then let's welcome Tom Baumbach, physician at TU Berlin, and he's gonna speak us today about the logarithmic Minkowski problem. Thanks everyone for joining. And before he starts, let me remind you all about our community statement. We are learning here. No one has all the answers, and everyone has something to contribute. That's very important to keep in mind. Otherwise, yeah, you can start.
Thank you. Yeah, and thanks again for the invitation. So I'm going to talk about the logarithmic Minkowski problem, which is based on joint work with Martin Henk, which is also my supervisor at TU Berlin. And this is, yeah, more or less a discrete point of view. So what I'm going to do in this talk, I'm going to first introduce you to the Minkowski problems. So I start with the Minkowski problem, and then we go to the logarithmic Minkowski problem. Then I'm going to describe the discrete point of view. And yeah, it's quite nice because last week I was able to prove a conjecture, and maybe if we have enough time, I can talk about that also. So I try to also put it in the talk. And in the end, I'm going to give a brief outlook about things that still can be done and other conjectures. Okay, so let's start. So the first Minkowski problem for polytopes is the following. By the way, if you do not know a lot of stuff about polytopes or convex bodies, feel free to ask. But this motivation is not super important to understand. It's just more like I'm going to show you some pictures so you can see what's happening. Okay, so we are given a set of vectors which are contained in the unit sphere, and you can think of these vectors as outer unit normal vectors of polytopes. And we are given scalars a1 and am, which are greater than 0. And then the question is, what are necessary and sufficient conditions that will guarantee the existence of an m-phased polytope, meaning that every vector ui really defines a facet of the polytope in M whose facets f1 to fm have facet areas am to a1 to am. So maybe we look at the picture first so everybody knows what's happening. So in this picture we have 4 outer unit normal vectors, u1 to u4. And then I didn't write down any scalars, but you could imagine that the scalars a1 to am are exactly the length of each facet. So where the vector is the outer unit normal vector. And then we ask, what conditions do these facets or lengths of these facets must suffice? And here is the answer. Minkowski also proved that the necessary and sufficient conditions are that the positive phi of u equals Rn, or the positive span. So the positive span is linear combinations of vectors where the scalars are all non-negative. And now the more important equation is that the sum of I equals 1 to m of ai times ui equals 0. So we see that it's more or less a linear equation that needs to be satisfied in order that we can guarantee the existence of such a polytope. Okay, the next step is we want to look at this Minkowski problem for convex bodies. And in order to do that, we have to introduce measures. And the Minkowski problem for convex bodies is the following. We are given a convex body K, and we have its surface area measure, which is denoted by S subscript K. And these measures are always defined on the unit sphere. So omega is now a subset of the unit sphere of dimension n-1, and it's defined as the Hesse measure from, and then we take the pre-image of omega, where we take the pre-image with respect to the Gauss map you don't have to understand everything. I would show you a picture and then I hope it gets clear what's happening. So in this example, we are looking at two-dimensional polytopes or convex body. So in the middle, we have a two-dimensional polytope. On the right-hand side, we have a two-dimensional convex body K. Then in order to look at the surface area measure, we now take a subset omega of the unit sphere here in the color red. And now we want to know what the surface area measure of omega is. First, we look at the polytope. So in order to get that, we look which outer unit normal vectors of the polytope are contained in omega. And if we go back these slides, we see that only U1 and U4 are contained in omega. So only these facets contribute to the surface area measure. And then the surface area measure gives the length of these facets. And now for the convex body K on the right-hand side, we look at all points in the boundary which have an outer unit normal vector contained in omega. And we see, so I printed it here also in red, I hope you can see it, but that's all points on the boundary of the convex body which have an outer unit normal vector in omega. And then we look at this line segment in this case and also want to know the length of this line segment. And that would also be the surface area measure of this convex body. So we see that it's generalized the polytope case to convex bodies, and now the task again is find necessary and sufficient conditions for finite Borel measure mu on the unit sphere, such that mu is the surface area measure of a convex body, meaning there exists a convex body K such that mu equals S subscript K. And not surprisingly, we have the same conditions. Just in the discrete setting. So in this case, the support of mu is not concentrated on a closed hemisphere, which was the same as saying that the positive half of the outer unit normal vectors spans the whole space Rn. And the second condition, you recall that we had a summation, and now because we are in the continuous setting, we now have an integral, which also should be equal to 0. And these two problems are well understood because they are characterized. And now we come to the logarithmic Minkowski problem, and first for convex bodies. Again, this time we are given a convex body K, and now we want to look at the cone volume measure of the convex body K. The cone volume measure is defined as following. So it's d subscript K of omega, and it is 1 over n times the integral now of the support function of the convex body. I've written down the definition here on the right again. And with respect to the surface area measure that we had on the slide before. So we can ask again what is happening right now, and I'm just going to show you an example in order to understand the definition. So the cone volume measure is again defined on the unit sphere. We are again looking at a two-dimensional example, so we are looking at S1. Here the subset is again defined, printed in red. And we again look at the polytope and at the convex body. So the cone volume measure first checks which outer unit normal vectors are contained in the set omega. Because now I have a different set omega than on the slide before. We only have one facet or one outer unit normal vector contained in the set omega. So we are looking only at one facet. And now the cone volume measure looks at the area of the facet together with the origin. So we take the convex half of the origin with the facet, and we look what areas it contains. For convex body K, we are doing nearly the same thing. We are just like in the surface area measure case, we are looking which boundary points have an outer unit normal vector contained in omega. Then we take all these boundary points and the origin and consider the convex hull and then we compute this area, and that's the Cohen-Borel measure for convex bodies. Here again, the task is to find necessary and sufficient conditions for finite Borel measure mu on the unit sphere such that mu is the Cohen-Borel measure of a convex body. That is, it exists a convex body K such that mu equals the Cohen-Borel measure of K. Surprisingly, this problem is very hard. So in general, there's no characterization whatsoever. But if we look at the symmetric case, so the symmetric logarithmic Minkowski problem, there's a fully characterization for that. What is the symmetric case exactly? We are now looking at symmetric convex bodies, so k equals minus k, and we also only consider even measures. So measure mu is called even is mu if mu of omega equals mu of minus omega for all measurable subsets omega of the unit sphere. Then there was a theorem proven by Minkowski, Ludwig, Yang, and Sang in 2013, which characterized the Cohen-Borel measure for symmetric convex bodies, and it introduced the subspace concentration condition, which will be pretty important for our talk later on, but I will always recall it when it's important. But here's the theorem: an even finite Borel measure mu is the Cohen-Borel measure of an n-dimensional symmetric convex body K, if and only if mu satisfies the subspace concentration condition, which reads as follows. First of all, for every proper linear subspace L contained in Rn, it holds that mu of L intersected with the unit sphere over the mu of the whole unit sphere is less or equal than the dimension of L over n times the measure mu on the unit sphere. And now we have a second case in which precisely equality occurs, namely equality holds for subspace L if and only if there exists a complementary subspace L prime, meaning that L and L prime form a direct sum of the whole space Rn, such that the support of mu is contained in L union L prime. Okay, now that's a symmetric case, fully understood, very nicely, but what about the general case? So if we have the non-even case, it was first proven by Alina Stancu some sufficient conditions in the planar case. Then in 2014, the discrete setting, the discrete measures in general position were also solved by Zhu. Again, we had some other sufficient conditions in the discrete case by Borel, Hegedes, and Zhu in 2016. Then it was proven that the subspace concentration condition is a necessary condition for centered convex bodies, meaning if we have a centered convex body which is centered at the origin, then the subspace concentration condition is always fulfilled. But we will see that later on again. Then the subspace concentration condition is a sufficient condition for convex bodies, but there are also non-uniqueness measures. I will not go into too much detail, but I was just thinking maybe it's nice to know. Okay, now we are going to look at the discrete point of view, which hopefully now makes everything a little bit nicer and simpler. And from now on, you should be also able to understand everything. Okay, what is the setting? We are now considering a polytope P, which is given as a hyperplane arrangement. So we have some vectors ui, which correspond to outer unit normal vectors, and we are looking at the hyperplanes ui at height bi and the intersection of all these. We also assume that the right-hand side bi is non-negative, which also implies that the origin is always contained in the polytope P. Remember, we want to look at cones where the origin and the facets are considered in a convex hull, and then we want to measure this volume. And we also consider the facets Fi, which are not always facets because they could be just lower dimensional faces, or if the description or the H description of the polytope P is non-redundant, then maybe it's even empty. Okay, so maybe we are looking at the picture to better understand what's happening. Here I have drawn 4 outer unit normal vectors, u1 to u4. So that's our starting point. Then we take a right-hand side, which is non-negative, and then we get the polytope P in the middle, where the origin is now contained. The next step is we are looking at the cones or pyramids with the facet Fi. So in our example, we have 4 different cones. We have cones C1 to C4, and we are now interested in the volume of these cones. And the volume of these cones is just a pyramid formula. So the volume is Bi over n, so the distance of the facet to the origin, times the n-1 dimensional volume of the facet Fi. And now the cone volume measure of a polytope can be written in the following way. Again, it's defined on the unit sphere, and it reads as 1 over n, which is just the pyramid formula, times the sum from I equals 1 to m from the Dirac measure delta ui. So if ui is contained in omega, then it's equal to 1, and otherwise it's 0, times the n-dimensional volume of the cone Zi. And I have also written it down in the pyramid formula on the right-hand side. Now, the discrete logarithmic Minkowski problem asks for necessary and sufficient conditions for measure mu, such that there exists a polytope P with mu equals the cone volume measure of P. And instead of looking at measures, we are now want to understand the cone volumes, or the volume of the cones, which you are now going to define. We are now going to look at the cone volume set. Again, we consider outer unit normal vectors, which should be of contained in the unit sphere, not in we also assume that the positive hull of U equals the whole space Rn, and that B is the right-hand side, which is non-negative. We need the assumption that the positive hull of U equals R in order to really consider polytopes, because we want to construct bounded polytopes, and they're only bounded if the positive hull of U equals Rn. Then, as on the slide before, we consider the polytope P of U and B, and then we define the cone volume vector gamma B, which is defined or has entries just like the cone volumes of each cone that we constructed. So, for example, the first entry would correspond to the outer unit normal vector U1, and then we consider the n-1 dimensional volume of the facet F1 times the height P1 divided by n. And here again, Fi could be empty of dimension less than n-1, which would correspond to the fact that this entry would be 0 in that case. Now we consider the cone volume set, which consists of all cone volume vectors with right-hand side b greater or equal than 0, such that all entries sum up to 1. In other words, the volume of the polytope B of U with right-hand side B has only volume equal to 1. And that makes sense because we only look at a partition of cones of the polytope P. So these cones summed up should be the volume of the polytope P. And we call this set the cone volume set of U. Again, I just wanted to quickly mention the symmetric case. So if we have a set U, which has outer unit normals in pairs plus minus everywhere, then we write US. So in order to, we call it the symmetric case. And for a right-hand side B, we write BI plus, if BI plus M equals BI, then we also write BS, and then we can consider the symmetric cone volume set. So we now have a symmetric matrix, we have a symmetric right-hand side, and again, we consider only polytopes with volume equal to 1. And here's a nice picture of in the symmetric case. So every outer unit normal vector comes in a pair plus minus, and all facets which are antidipole to each other, they have the same height. And here again, the symmetric case is fully understood by the subspace concentration condition, which reads exactly the same as in the measure case, but if we have polytopes, we can write it down a little bit nicer. Namely, if we have a polytope P, then the subspace concentration condition reads as follows. For every proper linear subspace L, it holds that, again, the cone volume measure of L intersected with the unit sphere Sn-1 over the measure on the whole unit sphere equals 1 over the volume of P. That's why you always consider in general only polytope swarm equal to 1, so we get rid of that. And then we sum up over all cone volumes, where the outer unit normal vector Ui is contained in this proper subspace L, and that should be less or equal than the dimension of L over N. And now it's pretty nice in the equality case, we actually now have a decomposition of polytopes. Precisely what I mean is, if equality holds in the first inequality for subspace L, then there exists a complementary subspace L prime, and polytopes Q1 contained in L and Q2 contained in L prime, such that we can write the polytope P as a direct Minkowski sum of Q1 and Q2. And you should remember this decomposition because that's a really nice fact, which we use in a couple of minutes. Now we look at the subspace concentration polytope. So if we look again, we have an inequality and we have an equality case. So we could just use these inequalities to define a set, and we will call the set the subspace concentration polytope. In order to distinguish these two cases where we have strict inequality or we have equality, we define two subsets. We define L of U, which consists of all subsets S of U, such that these are proper linear subspaces or correspond to proper linear subspaces in the sense that the rank of S is between 1 and n-1, and also we want that the set S is closed, which comes from matroid theory, and to write it down, it's just U intersected with the linear span of S equals the set S itself. Okay, this set should correspond to the strict inequality. And now remember, in the equality case, we had the decomposition of the polytope, and in order to write that down, we consider all sets S contained in LU, such that the linear span of S intersected with the linear span of the complement of S is trivial. In other words, the linear span of S and the linear span of U of the complement of S forms a direct sum of the whole space, and that should correspond to the decomposition. Now we define the subspace concentration polytope, and here again we want to publish a paper about it, and now we decided to define it a little bit differently. We now want that the strict inequality case on the bottom is now less or equal and no longer strict in order to really have a polytope. So, but how it's defined, we consider all vectors x in Rm such that these are non-negative they sum up to 1, so they should correspond to polytopes with volume equal to 1. And then we have these two cases for the subspace concentration condition. Namely, if we have a decomposition, then we have that the sum over all xi with the entry I, ui is contained in S equals 1 over n times the rank of S. And if we have no decomposition, then we want a strict inequality. And that corresponds exactly to the subspace concentration condition that we had on the previous slide. Yeah, also Liu, Zhang, and Yong looked at the so-called concentration polytope for U, but without antipodal points. And yeah, it wasn't too much of success, but they also wrote a paper about it in 2024. Now a nice observation for the subspace concentration polytope. If we consider a vector gamma contained in the subspace concentration polytope, and we consider the measure mu, which is defined as the sum of the gamma i's times the Dirichlet measure ui, so that delta ui of omega is 1 if and only if ui is contained in omega and 0 otherwise. And we know that this measure satisfies the subspace concentration condition if and only if this gamma is contained in the subspace concentration polytope, which is quite nice. Now, a theorem by Zhang, Li, and Zhu, they showed that the relative interior of the subspace concentration polytope is always contained in the cone volume set with respect to U. So if we have a vector gamma contained in the subspace concentration polytope, then there exists a convex polytope P such that the cone volume vector with respect to the polytope is equal to the vector contained in the subspace concentration polytope. Here, recall that in the symmetric case, we had that the relative interior of the subspace concentration polytope is equal to the relative interior of the symmetric cone volume set. I always have written it down with the subspace concentration condition, but now the subspace concentration condition is encoded in the subspace concentration polytope. So therefore we have this nice equality, but in general, we do not have a nice subset relation, and we also do not have equality between these two sets, just by looking, for example, at a trapezoid, as we will see later on. Okay, now a quick glimpse of the matroid theory. So Feichten and Sturmfeld defined the basis matroid polytope in 2005, and it's defined as follows. It's said P of U defined as all vectors x in Rm such that they are non-negative. Now the sum is not equal to 1, but it's equal to n. And they have no distinction between the two cases, equality and strict inequality. They just write down that the sum of xi is always less or equal than the rank of S for all S contained in the set L of U. And the basis matroid polytope is understood quite good, I would say. So we also have a vertex representation of it. And we can write it as a convex hull of all characteristic vectors of subsets S of U, such that S is the basis of Rn. And the characteristic vector means we have on the east entry 1 if Ui is contained in S and 0 otherwise. And from the definition of the matroid base polytope and the subspace concentration polytope, we immediately see that n times the, oh, not the boundary, I'm sorry, I meant the closure of the subspace concentration polytope equals the matroid base polytope. Due to that connection, we can try to use some matroid structure and we use this matroid structure on the separators. So if we call the set FU an element contained in the set FU is called a separator, and the set U is called irreducible if FU is empty. And then we have the nice structural result of matroid theory, namely, if we consider a separator V contained in the set FU, remember that means that the linear span of V together with the linear span of the complement forms the direct sum of the whole space. And then we can write the subspace concentration polytope as a Cartesian product of two subspace concentration polytopes with a right factor before it. But that's a nice decomposition, and this decomposition implies that it's enough to only consider irreducible sets U. Now we look at the cone volume set and also again at separators, and surprisingly, if we have a separator of the cone volume set, then we can also decompose it in the same way as we could decompose the subspace concentration polytope. Namely, we can write it down as the Cartesian product of the cone volume set of the separator and the cone volume set of the complement of the separator, again with the same scalars as we had in the subspace concentration polytope. Now here's the first consequence of this theory, namely that the affine span of the subspace concentration polytope equals the affine span of the cone volume set. And this, of course, implies that both these sets have the same dimension, and we can also compute this dimension. It's just the cardinality of U minus the number of irreducible separators contained in U. And now it's time for some examples. So first we look at the most simple example. We look at the orthonormal vectors U1 to UN plus 1, and we assume that they're in general position. With other words, we consider a simplex. And yeah, I've written down boundary again, but it should be the closure, I'm sorry, of the subspace concentration polytope. And we can write it down as the characteristic vectors of the linear basis of the whole space Rn. And here the linear bases are exactly any n subset of U. So we always leave out one EJ. Yeah. And the cone volume set of a simplex is the whole hypersimplex. So it's the whole convex hull of E1 to En plus 1. And this example shows that even though both sets have the same dimension, there could still be a huge gap between these two sets. Now we look at a trapezoid, which I also said in the beginning that this is a nice counterexample for the subset relations. So given pairwise distinct vectors U1, U2, U3, and U4, which we looked at in the beginning when we looked how we construct these cones, and we also assume that they're positively spanning, then we can write the cone volume set of this trapezoid in the following way. The first set is just the subspace concentration condition. But the second set is quite different. So in this, I don't want to read it out, but you see that in the last inequality, there's a root appearing, and due to that, we can see that this cone volume set is no longer convex, which is quite interesting because we recall from the beginning when we looked at surface areas, we saw that this is more or less a linear equation that they need to fulfill. So they also obviously are convex. But here, the cone volume set is no longer convex. So these problems, even though one appeared from the other, they are quite different, or they behave quite differently. And The closure of the subspace concentration polytope is again the characteristic vectors of all linear bases, and you see that the only missing vector is E1 plus E3, but because we assume that U3 equals minus U1, they of course cannot span the plane R2. And here again, in general, the cone-volume set is not convex. Okay, now we come to some structural results for the cone-volume set. So Liu, Lu, Zhang, and Jiong found some sufficient and necessary conditions for quadrilaterals, and these conditions are polynomial inequalities. So we asked if that's always the case, if we can always write down polynomial equations in order to characterize the cone volume set U, or in other words, is the cone volume set U a semi-algebraic set? And that is in fact what we have proven. So we proved that the cone volume set is a semi-algebraic set, and we call a semi-algebraic set is a subset M in Rn, and we can write the subset M as a union of sets X in Rn such that we have polynomials with a strict inequality and we have polynomials with equality. And yeah, then it's a semi-algebraic set. So what we need to do in order to prove that this is a semi-algebraic set, we need to find polynomials which describe the cone volumes so that we can write down these volumes of polytopes in polynomials. And in order to do that, we need some theory. Now it's a little bit more abstract, but I hope these pictures will help. So two polytopes, P and Q, in RD are called normally equivalent if and only if the outer unit normal vectors U always define a face of the same dimension. That is written down here. And then we write P is equivalent to Q. And for a better understanding of this concept, let's look again at the outer unit normal vectors of a trapezoid. So we have two possible types, more or less. So in the middle, we see a trapezoid. So U1, U2, U3, and U4 all define the facet of this two-dimensional polytope. And on the right-hand side, we have a triangle. We see that U2, U3, and U4 define a facet, but U1 does not. And that's why these two polytopes are not normally equivalent. And now our goal is to look at normally equivalent classes and then define some polynomial equations in order to get these volumes. And for that we need the following lemma. So the right-hand side, or the non-negative right-hand sides, can be subdivided into finitely many convex closed m-dimensional cones, such that the first condition is if we look into the interior of these two cones, these two polytopes with the right-hand side B and B prime are normally equivalent. And now the nice fact about these type cones is that there exist polynomials Vk, which stands for the volume of the polytope, and Fki, which stands for the volume of the facet, such that for any right-hand side B contained in the interior of a type cone, we can write down the volume of the polytope and the volume of the facet as a polynomial. That's exactly what we wanted. And the cones A1 to AL are the type cones of U, and as we have seen before, so in this case, if U is the outer unit normal vectors of a trapezoid, we have two different type cones. Namely, we have the type where it's a trapezoid, and we have the type where it's a triangle. Another example is, or another two simple examples are a simplex and a parallelogram, because they only have one type. They are always characterized by the outer unit normal vectors. Okay, and now how do we prove that the set is semi-algebraic? We write down the type cones because they are convex cones, they are polyhedra, and we find a matrix BK that defines this type cone. And then we consider the following set. Vk of u is defined as the tuple of gamma and b contained in r to the power of 2m, such that first of all b is contained in the interior of the type cone. That's the strict inequality. And then remember that we considered for a cone volume vector the entries where the n-1 dimensional volume of the facet, which is now encoded in this polynomial, times the height, so times bi over n. So gamma I is now the volume of the cone ci, which we defined in the beginning, and the polynomial bk of b should be equal to 1, since we only want to consider polytopes with volume 1. And of course, we only consider non-negative right-hand sides. Okay, and now a nice observation. If we have a tuple contained in the closure of the set bk of u, then we know that the cone volume vector with right-hand side b equals gamma. So the set bk encodes all the important information about the cone volume set. And with that observation, we can prove that the cone volume set is the union of projections onto the first factor of these sets vi. And therefore, since bk is a semi-algebraic set, since it's defined by polynomial inequalities, and semi-algebraic sets are closed under projections, the cone volume set is also a semi-algebraic set. Okay, now a conjecture which we are not able to prove, but I still think it's true, and is the following. So the set Vk is in fact a manifold, and the conjecture is that the boundary of this manifold has non-positive curvature in the first coordinates. What does that exactly mean? For example, if we consider the trapezoid, the cone volume set of the trapezoid, and we factor out only the first coordinates, then we get the following representation of the cone volume set. So it's the union of these two sets, and we can see that it's always curved inwards, but it's never curved outwards. So I would call this a concave set in contrast to a convex set, because the convex set has always non-negative curvature, but I think the cone volume set or the manifold has always non-positive curvature. So it's the exact opposite of a convex set. But yeah, we were not able to prove it yet. Hopefully in the near future we are able to do that. As you maybe remember, in the symmetric case, we always had equality between these two sets of the surface concentration polytope and the cone volume set for any outer unit normal vectors u, as long as they are symmetric. Now what's quite surprising is that in the non-symmetric case, we only have equality if and only if the set u that we consider defines a parallelotope. With other words, u is linear equivalent to plus minus e1 to plus minus en. And yeah, then we can also compute the cone volume set in that special case. Namely, it's the Cartesian product of one-dimensional matroids, more or less. The proof is rather complicated, but I still want to give you some insights on how to do that. As we have seen, hopefully now, that the structure of the cone volume set U depends strongly on the outer unit normal vectors U. And therefore, we want to analyze the structure of sets U which positively span the whole Rn. And now, to make it even a little bit nicer for us, we only consider positive bases. And a positive basis is a minimal positively spanning set. In other words, we consider a set U contained in the unit sphere such that the positive hull of U is equal to a linear vector space. And then we say that the set U is a positive basis of L if for every proper subset it holds that the positive span of the subset no longer spans the linear space L. Further, we call U as the simplistic basis of L if the cardinality of U equals dimension of L plus 1. Here are some examples. So the outer unit normals of a simplex form a simplistic positive basis of Rn. Remember, simplex sets exactly n plus 1 facets, and these outer unit normal vectors are then the simplistic positive basis. Also, I think what is quite obvious is that the set of vectors plus minus E1 and plus minus En is also a positive basis of Rn, but of course it's not simplistic because the cardinality is always 2n and where the dimension of Rn equals n, yeah. And for another example, which is not a positive basis, we consider the outer unit normals of a trapezoid again. And then we see, of course, they span the whole space R2, but if we leave out the vector U1, they still span the whole space R2. And that can also be seen because they define a triangle in the plane. Okay. So, and we now want to focus on positive bases because they have a pretty nice structure, because there was a result by Ramonovsky. Sorry for pronouncing that name. And that theorem is quite old, but it has really nice, it gives a really nice picture of positive bases. And a set U is a positive basis of Rn if and only if U is a simplistic basis of Rn, so it's a simplex, or U admits a partition in the following way. So we can write U as a disjoint union of sets data 1, union data 2 plus vector Ci, all the way up to data R plus a vector Zr minus 1, where data 1 until data R are simplistic bases of the subspaces L1 to Lr. The dimension of these spaces is at least 1. And further, it holds that Rn is a direct sum of these subspaces. So how you can think of positive bases right now is they are just a union of simplistic bases. So that's how I'm thinking about positive bases. To be honest, I'm now defining the set U delta 1 to delta R, which is just the union of delta 1 until delta R, which is, we just forget about the right-hand side, the shift vectors, Zi. And it holds because we have now decomposition of the whole space Rn via the subspaces L1 to Lr, that the cone volume set of the set is just a direct sum of these cone volume sets delta I, and because these are simplicial, we also know how they look like. We can write down as a convex hull of these vectors. So it's a nice, easy way to get some information about the cone volume set. Maybe let's look at an example for simplicity decomposition of a positive basis. So we have the set U written down as above, but I also try to give some graphics so it's easier to understand what's happening. So on the left, we see a geometric interpretation of the set U because we just picture it as a pyramid with outer unit normals in U, where the base of the facet, which is here on the top, is defined by the vector U1. Sorry. Now, I wanted to get rid of these shift vectors. In order to get rid of these shift vectors, I'm looking at the set U delta 1, delta 2 with a right-hand side B. And what's happening is we saw that these are direct sums, so they are orthogonal to each other. And we now have now a nice sum of two simplicities, namely we have a triangle plus a line segment. That's basically what is happening if we forget about these shift vectors. And if we consider now the polytope B with the same right-hand side B, but now we do not forget about the shift vectors, so we consider the set U, then we have this polytope on the right-hand side, which is a little bit, I don't know, it's not really nice orthogonal, we cannot really picture it. However, if we stretch out these polytopes and make them super thin, they will converge in the Hausdorff metric. And that fact allows us to conclude that the cone volume set of this set U delta 1 to delta R is always contained again in the closure of the cone volume set of U. So we have some nice subset relations now, which imply some nice results, I would say. For example, it also implies the result that we have equality if and only if U defines a polytope. But there's a problem with this approach, because there will always be a dimensional gap between the set on the left versus the set on the right. So we always have a real difference between these dimensions. But nonetheless, these are nice subset relations which we can use to prove some stuff. Okay, I have 6 more minutes. Maybe I'm able to also talk about the pyramid structure of these cone volumes. So the pyramid structure has the goal to analyze the case that the vector EI is also contained in the cone volume set of U, because we know that the cone volume set is always contained in the hypersimplex, and now we want to know under which circumstances is the vector EI contained in the cone volume set of U. And for that, we give the following definition. We define the set U delta, which contains of all outer unit normal vectors, so that P with U and right-hand side B is a four-dimensional pyramid with space defined by U, and right-hand side B, which is non-negative. And to understand the set a little bit better, we consider again the example from before. So we have the same outer unit normal vectors, therefore we get the same pyramid. And as I told you already, the top facet is defined by UI. So U delta always consists of U1, sorry, but it's also the only vector which is possible to define a pyramid with the other outer unit normals U2 to U5. And then we have the nice following observation. It holds that UI is contained in the set U delta if and only if the vector EI is contained in the cone volume set U. So we have encoded now these vertices with the set U delta, and we also can give a characterization of U delta with the help of positive basis. But I would say that's out of the scope for this talk. But one more nice or interesting case is an inequality for the elements in U which are not contained in U data, so they are not contained in the pyramid structure of U. And the question was, can we characterize the outer unit norm its UI such that the limit process of these cone volumes gamma U with right hand side En converges to this vector EI. And I was able to prove this last week, so I'm quite proud, and I wanted to talk about it a little bit. If we now consider outer unit normals U, then there exists a scalar epsilon subscript U, which is strictly greater than 0, but it still depends on the set U. Hopefully in the near future I can prove that it's independent of the set, such that for all U which are not contained in U data, I'm sorry, there's 2 negations, but there should be only one. It holds that the cone volume vector with respect to the entry U is always less or equal than 1 minus epsilon U. So what this tells you is, if you can get super close to the vector EI, at some point you will have a pyramid. There's no other way than you have a pyramid at some point. And if not, then you are always strictly away from this vertex. So why do I hope that this epsilon U is independent of the set U? Because in the planar case, I can prove that epsilon U can always be chosen to be 1/2. And in the dimension 3, I can prove that for positive basis, epsilon U can always be chosen to be 2/3. So we assume that in general it should have some form of n-1/n, which would be quite nice. But yeah, it's for the future. Okay, to answer this question, on the top, the limit only holds if and only if UI is already in the pyramid structure of U. That was, I think, all. Just a little bit of outlook. We still hope to prove that the cone volume or the convex hull of the cone volume set is a polytope, meaning it has only finitely many extreme points or vertices, which also corresponds to the fact that this manifold is concave. If that's true, then that should also hold. So that would be a nice, that would be a nice proof for that. And if we have a positive basis, then we have the following convex representation. But I think it's 1 hour. I'm done. Any questions?
Wow. Okay. Thank you very much. It was a lot taken for sure. Yeah. Unfortunately, the co-organizers had to leave early because of this time difference. Has anyone any question? So, okay, let me end the recording then, and right.